Well, so 1 minute, I'm going to plug my laptop in first, so we don't encounter any more technical hitches throughout the course of this talk. Well, at least once I do my laptop turning off. Okay, so okay, it's over there, but it should hopefully appear over here as well, because otherwise I'm going to be a long way away from my computer with quite short arms. So let's wait for this to come back on, and then things will flow a lot more smoothly, hopefully. Okay, here we go. Okay, thank you. Yeah. Okay, so if anyone's been to any of my talks before in the past, you'll know that they usually contain a diagram of how GHC works. So over the years, I've now managed to refine my diagram to something that I think is understandable by any Haskell programmer. So this is how I think most people think about how GHC and the executor works. You give it an input, which is usually a program, and it produces an output. Okay, great. Everyone's happy with that. We don't need to know anything complicated about the internals today, about all the different passes and all the compilation and stuff. That's all right. So in my experience of writing Haskell, what this actually usually means is the input is category theory, for better or worse, and the output is unit. So what's actually going on inside is usually not greatly of concern to these people, as long as it computes them their single, distinguished, unique value that they desire at the end of the compilation. So, however, I have since learned some more things about programming, and we don't just care about the actual result that our program produces, we also care about other external things that happen, such as how long the program takes to run, and also how much memory the program uses as it is operating. So GHC is no different in this regard, and people do at least claim to care about how much time GHC takes to compile their program and how much memory it uses. So this talk is about memory usage and analyzing the memory usage of Haskell programs. Because in general, what happens when you have a Haskell program which is using memory, the memory tends to increase in this semi-monotonic fashion, and we're just left with questions about why the memory usage is increasing and what we can do about it. So we're going to try and, in this talk, look at some techniques we can use in order to firstly analyze what the memory what the profile of the memory actually is, and then some more precise techniques about how to possibly fix the problem. So firstly, we're going to look at some general space profiles to get an idea of the problem. So the first half of this talk might be quite familiar to some experts in this room. We're just going to look at the standard space profiling tools already built into GHC. But in the second half, we might get into some more complicated stuff. So fall asleep now if you already know this stuff, but wake up later, please, when I start getting into GDB and all that fun stuff. Right, so if no one's seen a space profile before, this is generally what a heap profile looks like if you get one out of a HaskellX executable. So on the bottom here, you have the time the program was taken, and on the vertical axis is the current residency of the program at that specific time point. So how the profiler works is at a certain interval, which is usually like 0.1 seconds, unless you modify it, it takes a complete census of the heap, and then it looks at each thing that it's seen on the heap and puts it into a certain bin. And which bin it chooses depends on the profiling option. So in this particular example, this is about the closure type, but we'll see some more different examples of how GHC can actually analyze the different closures on the heap with some profiles later on. But this is just if you've never seen a heap profile before, this is what it looks like. So you have the time and you have the allocation, and each of these different bands is something different that we might care about that's going on the heap. Okay, so how do we actually make these profiles if you've never seen it before? Well, the most low-level way is it starts with a two-step process. So step one is you make sure to compile your executable with the -prof option if you're using GHC directly. And then once you have your executable, in order to generate the profile, it depends on what the additional options you pass the GHC RTS at, when you're actually running the program. So in order to generate the profile we saw before, you firstly compile your executable with -prof, and then if it's called main, you run it with -h, and that will produce a .hp file, which you can turn into one of these graphs that we've seen before. So most people, apart from me, are not actually using GHC directly in order to compile the program. So these days, it's actually really straightforward using Cabal as well to do it, and probably Stack, although I don't know. And using Cabal, all you do is write profiling :true in your Cabal.project file, which will instruct GHC in order to compile all the dependencies with -prof and all your project -prof and everything with -prof that could possibly need it, and also turn on some cost centers. And then when you run the executable, you can just use Cabal new run with the executable, and then pass the RTS option as you would do before. So setting up your executable to be profiled is actually not that difficult to achieve. So for this talk, I had to pick an example of something that I wanted to profile. And the thing I wanted to profile was the GHC executable itself, which is a Haskell program. So we can just use the normal Haskell profiling tools in order to profile GHC, in order to try and answer some questions that everyone in the whole world has had. Why is GHC use so much memory, and what can we possibly do about it? Okay. So in particular, the executable that we're going to profile today is this simple GHCI application that I've constructed, which all it does is firstly set up the environment that we're going to compile the modules in, and then it just compiles the project. So all this does is it takes the front-end part of GHC and puts it into its own program, so we can compile it with -prof and get the profiling output out. So you can't normally profile the GHC executable, but with this simple wrapper, you can. So you can actually try it at home if you have a slow program and want to work it out. OK, so in order to get the options to actually pass to the GHC executable, I use Cabal. So the thing we're going to profile is GHC compiling Cabal. So in order to do that, we need to get the options that we need to compile Cabal, which are actually reasonably complicated. So if you call Cabal with the extra verbosity flag, then it gives you all the options which you need in order to set up a session. So I did that, got this file full of options, specifying all 240 modules of Cabal, all the different flags and package databases that Cabal uses, and all this extra stuff. Put it in a file, and then we can use those with the executable that we defined on the previous slide in order to create these space profiles of GHC itself. So the only reason I'm using GHC is because it's a project I'm familiar with, and I thought it would be interesting for people to see what is actually going on internally on the heap. OK. Right, so now I've got to go to my other slide deck, because you may have noticed now my aesthetic is these rounded rectangles, and Google Slides, great rounded rectangle stuff. But where is it? OK. But I wanted to also embed some HTML, which was impossible, so not that picture. No. OK. OK, here we go. Right. OK, so now we've set up all our profiling infrastructure, we're going to actually do some profiling. OK, we're going to do some profiling of GHC. And recently, I wrote this new profile viewer, which is called event log to HTML, which instead of the old, if you've ever done heap profiling before in Haskell, you've probably used HP to PS and created this monochrome heap profile, and then I had to pass the -c flag in order to make it colored. And you get this tiny PostScript file out the end. You've got to convert to PDF, and things are pretty horrible. But now my new profile viewer provides these interactive profiles, where you can hover over each band in order to see which specific things are allocated. And you can also there's also these other different profiling modes, which I'll talk to in a bit, and also click on the bands individually to isolate each part of the allocation individually to get a more precise idea about what actually is going on. So if these profiles look a bit fancier than usual, that's the reason why. Right. So I sat at home and I started my executable and passed the plus RTS dash HT dash L I2 options to GHC, and that created the information for this heap profile. What is this telling us? Right, the dash HT option breaks down the heap by closure type. So every closure on the heap has a specific type, and this profile breaks it down by those types. So it's potentially a bit more low level than anything you find in your Haskell source program, but it's usually a great idea to get a really precise idea about what actually is happening. So what is this top band here, this big green band? Well, we hover over it, we can see these are GHC prim ghc.types.cons. So the number one source of allocation of GHC compiling cabal is lists. So, which may not be any surprise to people who have had similar issues in their own applications. So we have 152 megabytes of list conses, which is quite a large number considering when each one is only 3 words each. We'll come back to that. And secondly, we have 112 megabytes of tycon app. So that's something internal to the representation of types in GHC. Again, each one's only 3 words, so why is there 112 megabytes of them? We'll come back to that later. And then we have these bands down here, which are things like what we have: iface type, iarg, iface type, iface tycon, iface type, iface tycon, something else, and so on and so on. And these all appear to be correlated with each other and contribute about 105 megabytes in total. So we can see if they're correlated by going over to this view, and this view here shows you the percentage, total percentage of memory usage of each band over the course of the program. So they're all rising about the same rate, and it indicates that, well, at second 100, there is 50% of the total maximum that they'll ever allocated. And at the end, you see they all just get more and more throughout time. So at the end, the highest point. OK, so we started off getting this reasonable idea using the closure type. And one of the big advantages of using this closure type profiling is that you don't actually need to compile with profiling to get it, because all the information about which type each closure is already present on the heap for all programs. So if you want to get a reasonable idea before you start recompiling all your dependencies and taking about 5 hours using -prof, then you can use -ht in order to start out your journey into profiling your Haskell executable. OK, so why are there so many lists? Why are there so many type constructors? We'll come back to these questions later. So profile number 2. OK, we've got this low-level view now of like what sort of stuff is on the heap. The next profile I usually turn to is the HY profile, which is breaking down the heap by Haskell type rather than the closure type. So before we had specific things like listcons, tycon app, like all the specific names of data constructors. But HY is a bit more high level and shows you the types rather than the data constructors. So number 2, the profile looks quite similar. And the number 1 band is still lists, which is not really surprising. But now if we look down, the tycon app band is now just type, and it hasn't actually got that much bigger. So we can see that tycon app is the primary source of the type allocations in the program. More interestingly, or perhaps not, but you also have this int map. Int map is now one place higher than it was before, which I noticed when I was looking at these profiles, because that is a combination of, so int map has 2 constructors, bin and tip, and so bin and tip combined together produce 44 megabytes. And we have byte strings, and then all those iface types are combined together now, and iface apargs, and so on. So this gives a bit of a high level, and you can see whether, if you just use the HT profile, you can see if one constructor's contributing a lot, but with HY, you can see if one specific type is contributing a lot. Neil?
Why can't GHC produce this from the same information it has in HT?
Yeah, question, yeah. So the question is, why can GHC not produce the breakdown by type based on the information in the HT profile? And the answer for that is what type a closure comes from is written in the profiling header. OK, so the profile, you don't need the profiling header for the -ht profile because that just reads off the type of the info table. But what -prof does is it adds an additional word to every closure, which points to the profiling header, which contains all the additional information. It contains what module, what type, what cost center stack it comes from, and all the additional information that we'll see in the other profiles. Does that answer the question?
Yeah, but I would have thought that word could the closure information could then point at the type information, so you wouldn't need any more words to still get this information.
Yeah, but then you have the overhead of storing the type for the Haskell type for every closure.
But it must be storing the string for every closure already.
Yeah, only with -prof. But with HT, that information is already just in every Haskell program.
The string name of the closure?
No, well, yeah, okay.
Maybe.
Yeah. Yeah, some information is, I need to look at -ht and see actually how it's implemented to answer that question. I can't answer it right now. Okay. Okay, so lists and types are still dominant. Nearly all the type allocations are from type-map, and we could also see, which I forgot to show you, that actually with this profile, if you select lists and types together, you see that the spikes happen in the same place. They rise at roughly the same rate. We look at lists and types over here as well. We see that they're basically correlated with each other. So, we have some indication now that lists and types, like they cause one another in some way to happen, which makes sense because type-on-app mentions lists. Okay, so we've now got a general idea of like what sort of stuff is causing issues for us. But what if it's actually all stuff that is useful? Like, what if she actually is using all this stuff, all these lists and types? I mean, it is plausible, although unlikely. So the biographical profiler tells us about the life cycles of our closures. Okay, so this is an example of a biographical profile. It's split into 4 bands: void, drag, use, and lag, and inherent use, 5 bands. So void memory is the biggest one, and void memory is memory that is never used at all. So, so we have a nice fat band here, 455 megabytes of memory that's never used on this specific execution of GHC compiling cabal. In theory, for this specific execution path, we didn't need to allocate any of this memory in the first place. Then the drag memory is also somewhat redundant because drag is memory which is used once but then not deallocated. It's retained in memory after it's used. So we have, by the end, we have 159 megabytes of closures which were used at some point but were never garbage collected. So the use band is quite small. And that's, it's not using very much time. And lag is also quite small. Lag is stuff which is allocated before it's used. So we could, in theory, allocate it later. But this is quite a small one. So mainly here, we care about void and drag. And like, why is it like there's all this stuff which is not used for this particular execution path. So most memory is not used, but maybe there's a reason for this, right? So this profile, it can be shocking. It got a reaction from the audience, which is the primary benefit. Yeah, Ollie.
What do you mean by used? Like, why would I have memory that is not used? How does that happen?
It can be allocated, but if the closure is never entered,
Right.
then
So they kind of evaluate funds?
no, not necessarily.
Okay.
But if you like just write something and you're like, if for example, right, okay, if you put something in a cache, for example, and if you like, and then you never actually get the thing out of the cache, then it'll be void memory. And it's not a thunk because you evaluated it before you kind of made it and then put it in the cache. But it could also be a thunks as well. So so there's 2 reasons why you might get void memory that is not worrying. This only profiles one execution path. So there could be some other execution path which does use all this stuff eventually, but it's impossible to see from one run. And a typical example of this is for error handling. Like, you see this in applications all the time. Like, the application keeps around all this additional state and retains loads of stuff because at some point in execution, it needs to handle an error. And you usually are profiling the happy path of your program. So you can keep a lot of stuff around that you don't actually need until this failure happens. And the second case is if you're creating some kind of cache, like you usually put more stuff in the cache than you actually ever need, because the whole point is you can't really predict what you're going to need, and that is actually, I think, what's happening inside GHC, although I haven't fully got to the bottom of the matter. OK, so we've used these 3 profiling modes to get some indication, and now the final profiles we're going to see are combining together 2 profiling modes, which is a really, really useful technique. So we've seen this void memory, and now we're going to use the combined together HB and HD to get a profile which just shows us what the void fragment of our memory is, and so what actually is the stuff that is never being used. So I passed the HB void flag to the RTS and the HD flag, and that gave me this breakdown which said, OK, most of these lists are not being used, but it seems like the Tycon apps actually are being used, which is good. But then we have all this IARG, iFace Tycon, all these stuff that we saw before, which doesn't appear to be used. So now we've got an idea of, firstly, that we have a problem, and we have a bit more of an idea of the stuff which is causing the problem. Finally, we can also combine together HB and HC. So HC is the cost center profiling mode, which I haven't really talked about yet, but it can give you an idea of where in your program the memory is actually being allocated. So I'm always very skeptical about this view providing correct or useful answers. But it can be useful to get some indication. So GHC has these cost centers defined. And the 2 main ones here are both about making interface files. So if we recall the previous profiles that we saw, some of the main indicators were things like iFace Tycon, iFace ARGs, and all this stuff. And then the cost centers point us to the point where the interface files are made. So it seems that GHC is making the interface files, caching them, and then never deallocating them. So that's the theory that we're going to go for now. OK, right. Thank you, slides, for keeping me on the straight and narrow. Back to my happy rounded rectangles now, and as a special treat to myself, we have a lot of rounded rectangles on this first slide. So just to recap, we saw these 4 profiling modes, and they told us different things. So we've got a general idea. Then we used some slightly bigger buckets to check if there was any small bands which added together would have caused some more cause for concern. We checked the life cycle of the closures using HB, whether something is used or not. And then finally, we used HC to check where this unused memory is actually being allocated from. So these are some of the things they told us. We have these Tycon apps and lists, and most allocations come from Tycon app, and all this stuff. So we've got this information. What we need to do now, OK, we've got to combine it together, use our brains into this knowledge gained from profiling, and finally turn that into using some main knowledge, work out where the problem is in our program. These profiling modes are not going to tell you usually what exactly to fix. It gives you the idea. And then you have to use the idea yourself, think about it a little bit, in order to fix the problem. So I know in GHC that these two potential caches which might be storing interface files. And one of them is the home package table. One of them is the external package state. The home package table stores interface files for things that we're currently compiling. So it's things in the Cabal library. An external package state contains interface files for things which are in external packages. So both these things potentially are a cache, and both of them contain interface files. So now I need to work out which one is the problem. So usually the old way would be then just look at your program and find out what's going on. But now there's this new patch by Daniel G, which has a new profiling mode to try and answer these kinds of questions. So how this patch works is you're allowed to use a specified routes to specific things in your program. So the first step is that I add 4 routes into my program, one pointed to the home package state, one to the external package state, one to the finder cache, and one to the name cache. And then I spin up the program with the RTS-HO flag, and it tells me how much memory is accessible from those specific routes. So this allows you to create much bigger bins and see everything that is underneath that bin for however much you want to see. OK, so this wasn't actually as conclusive as I thought it would be when I started doing the experiment. but I wanted to show an example of using this profiling mode. So this big band up here is things that are allocated in the external package state. So you can see that the external package state retains a lot more memory than the home package table potentially. And then you also see you have these smaller bands here, which are to do with the name cache and finder cache. But mostly it's stuff like in the external package state, which is not in the name cache or finder cache. So it wasn't that conclusive, but it's an interesting little new mode that I just wanted to put on here because I tried it out, and hopefully, if someone thinks this would be useful in their programs, they can contribute on the merge request so it can get merged for 8.10 maybe, if it gets finished. OK, so how are we going to fix this problem now? Right, we have a cache. The idea to try and fix this that we have is to use compact regions. So we're going to try and offload the cache into a compact region. So, which are the benefits. Firstly, so we don't traverse it by GC anymore. Like this cache contains lots of lists potentially, which add a lot of pressure to the GC, and it never changes, and it's always retained. So we might as well stick in a compact region. And secondly, you can serialize and deserialize compact regions really quickly. So potentially we could even unload the cache completely and reload it when it was actually going to be used. OK, so that's the first part of the talk, using profiles. So if anyone has any questions about the old space profile, yeah, go on, Eric.
Sorry, not so much about profiling, but about those regions and having caches in general. Is there a library that uses compact regions and offers like a nice cache API that could be reused everywhere?
No.
Wouldn't that be a good idea?
Well, it would be a reasonable idea, yeah. So I only know one project that actually uses compact regions. One public project that uses compact regions, which is HNX. So HNX uses compact regions to serialize their interface files. Rather than using they also have a binary mode, but they use compact regions to if you're just doing it on your own computer, then it's a lot faster to serialize and deserialize them. So I don't know if they've created a nice API, but yeah, I don't really think so. No. OK. So we've seen these profiles give us a good general idea about what's happening, but it still required my immense brain to try and work out what was going on. You can't really use them to see what precisely is happening. You get this general idea, but the bands are too vague. The modes are not precise enough. If you tea leaves, if you think you're seeing something useful, you're actually not. And also you have to keep rerunning the program to get different information out, which can be problematic if your program takes a long time to run. Even longer than GHC, potentially. I've been told there are ones. So now in phase 2, the research direction, we're going to try and find some precise techniques to fix problems in GHC. OK? We want to ask precise questions, and we want to find precise answers. So I share an office with the computational neuroscientists, and this is what I imagine that they do in their day-to-day lives. So I felt a bit jealous. So here I am, Pickering GHC dev with my lab coat on, and what I want to precisely look at is the heap. And the tool that we're going to use at first to answer these questions is GDB. So people may not expect me to hear a talk about using GDB at a Haskell Exchange, but it's actually quite pleasant to use GDB to ask these. You look skeptical, Neil.
You said pleasant to use GDB.
Yeah. Yeah. OK. All right. Yeah. My perspective is probably a bit skewed at this point about what pleasant means. But I found it wasn't the worst thing I've ever done. Right. So we're going to use GDB to try and answer one precise question about our heap. And the question is, why are there so many Tycom actions allocated? So over the course of GHC's lifetime, no one really knows anymore where all these things are allocated from, or what the call sites are, or anything. So, it's probably the same in a lot of big applications. You have a problem, you have lists, or Tycom app, or something big, and it's kind of hard to understand, begin to understand where they all come from. OK. So, Neil is right, it's potentially not pleasant. You have to dodge these lasers when you're in GDB to avoid segfaulting your program. But if you just stick to the simple 3-step plan, then we'll hopefully avoid the lasers today. So step 1, we get the address of the info table for Tycom app. And we're going to use that in order to find all the occurrences of TiconApp in the entire heap. So that's step 2. Ben Gamari has written these great functions for analyzing the heap in GDB. So GDB has this Python interface, and Ben has written these functions in Python, so you can traverse the whole heap in order to find out this sort of information. So the next step is we get all the TiconApp closures into a big list, and I actually sampled this list, so we only have 100,000 TiconApp closures rather than however many there are, 1.5 million or whatever.
What is GDB?
GDB? Yeah. Oh, sorry, yeah. So GDB is a debugger that you're meant to use for C programs, I believe. You can use it for other languages, like Haskell. And, I mean, what other languages do people use GDB for? Rust? C++, yeah. It gives you like a very low-level way to poke at memory and all this sort of stuff. Sorry? Yeah, GNU debugger, yeah. Yeah. So yeah, the purpose of using GDB is it allows us to directly access the memory and traverse the whole memory using some kind of interactive method rather than I don't know what else you would do. I mean, it sounds complicated, whatever else. Right. So the result of calling these Ben scripts is we get a list in Python of all the pointers to the Ticons that the Ticon apps are applying. So Ticon app is a type application of a type constructor to a list of arguments. So what I've got now is a list of all the Ticons that are applied to some arguments. And we want to see what those actually are so we can get an idea of whether it's actually necessary to allocate all these different Ticon apps. OK, so yeah, the link to the scripts are here if you want them. Right, so we crunched the numbers, and we could get these addresses, and we're like, OK, so the number 1 out of 100,000 closures, 28,732 of those arise from the same application of the same type constructor to the same arguments. And out of 100,000, this is a bit worrying, because why do I have 28,000 of the same one? Surely there are not 28,000 distinct applications to distinct arguments. So I thought we could probably reduce this number somehow. And if we can reduce this by a quarter, then we'll reduce memory usage by a quarter as well. I'm thinking that we had 150 megabytes of memory from Ticon apps before. This could be significant and quite easy. So in order to do that, I want to find out what the name of the Ticon is, right? But all I have is the address to the Ticon closure. That's not particularly ideal. Like I can't query GHC. It's like what Ticon is 0x45f35 blah blah blah. So at that point you've got to you've got to do a bit of pointer traversing, and you get down to the name and then the occ name and then the fast string. And once you're at the fast string, you can the fast string is the name of the Ticon. So now I've got the address of the fast string. I just need to look at the byte string inside the fast string in order to get the actual name. All right, so that's a bit complicated because the byte string gets unpacked, and then so you have this bit is the fast string, this white bit, and the byte string is in red here. So the bit that we actually care about is over here. It's the address of the byte string with the offset and then the length of the byte string. So yeah, so get those things. Right, those are the addresses. You add them together, you're doing all this arithmetic. It's like, you're a hacker. I'm a hacker, finally. I've been throwing Haskell the whole time, but now I'm a hacker. It's perfect. So I'm adding an offset to a pointer. Look at me go. And I get another number. I'm like, surely this is wrong. Surely this isn't going to work. And I look at the contents and I'm like, OK, yeah, right. Yeah, 0x. What is this? Like, maybe it's right. OK, it's 4 things long. OK, so it's 4 things long. Maybe it's those 4 things. Yeah, maybe, I don't know. I don't know if this is, it could be just any bit of memory, couldn't it? Like, who knows what's going on? Right, so, all right, the first one's, OK, 65, that's E. OK? OK, that's good. That's an ASCII character, yeah? Yeah. 70 is P. OK, yeah, we're getting somewhere. 79 is Y. Right, so E, what type constructor is E? Don't type constructors have to start with a capital letter? Like, what's going on here? Like, it's a T. Oh my God! Like, Okay, I got the right bit of memory, yes, the beauty of slides. So, yeah, this is backwards, isn't it? Yeah, great, okay, right. This is the type constructor, all right, great, we've made some progress here. So 28,000 of these allocations are type type to the empty list. Type has no arguments, so we have 28,000 identical occurrences of the same closure on the heap, which we just don't need to have. They're all the same. Why are they not shared with each other? So I made this ticket, which is GHC wastefully allocates thousands of type blah, blah, blah nodes. Simon says, good idea. So, yeah, I know, Simon, yeah. Think of the pain that I went through to correctly add an offset to an address to get to this point. I don't mention that part in the ticket, you know, I'm a humble programmer. But overall, once we end up sharing this common occurrence, we can reduce the allocations of GHC by 20, well, not in total by 25%, just this one small case by 25%. So a small victory for man, but you got to take everything you can get when you're in this world. You know, it's dog eat dog in it, so you got to just do the bit you can. Okay, so then that was an example of a precise technique that I have used in order to find a space leak. But kind of the point was, you guys don't really want to do that, do you? Like, you didn't even know what GDB was. Like, that's good. I didn't know what GDB was until I thought, how am I going to fix the problems? So I had to learn how to use GDB in order to use it to debug Haskell programs. So towards the future, perhaps we would like a better way in order to precisely analyze these queries, specifically for Haskell programs. Okay, and that is what GHC debug is aiming to be. So GHC debug is aiming to be a version of GDB specifically for Haskell programs. And how does this work? Well, the idea is that the program that you want to debug creates a socket. When the RTS starts, it creates a socket, which can then be connected to by the debugger. The debugger can then request information about the heap over the socket. So it can request things like what closures is at this address, traverse the whole heap and find all the type and app constructors, what is the info table of this thing, and so on and so on. So all these specific queries about Haskell's heap layout will be encodable as Haskell programs. So you write a Haskell program in order to debug the heap of a Haskell program, okay? Which hopefully is a lot more comfortable to people in this room, because personally, well, I used to at least, prefer writing Haskell programs to manually adding pointers together and all that stuff. So I've been implementing this library with Ben Gamari as well. And I've had a few external contributors, and things are looking promising that this will work. So hopefully by 8.10, my patch gets merged to GHC, which enables this library to just be all in userland, and then once we're there, anyone will be able to use it with their executables. Okay, another technique that people have used and hope to use more in the future, these weak pointer techniques. So Simon Marlowe famously used these to find some space leaks in GHC. So the idea of a weak pointer is not a route for garbage collection. So normally, if you have a pointer from one object to another, that means that the child object is not garbage collected because there's a reference. But a weak pointer points to another object, but does not count as a route for garbage collection. So the idea is that you create weak pointers pointing to things that you believe should be garbage collected at a certain point, and then when you believe they should have been garbage collected, you check to see if the weak pointer is still pointing at the object. So we've used these in Haskell IDE engine a bit to try and work out like why certain things weren't being cleared from caches and so on, which worked quite successfully. And I've been working on this with Luke Lau. On the left here, and the library is called, well, the library to add these weak pointers using generics is called DiePack, which we haven't, it's work in progress still. The Rust thing works, but we need to push it further. So just final few ideas, heap snapshots. Like if you're a JavaScript programmer, then you probably know that like most JavaScript engines allow you to dump a heap snapshot at a certain point in your program, which you can then look at later to analyze the structure. Like we could do this in Haskell as well, and I think it'd be quite useful. So we're going to try and do that. And once you have heap snapshots, then I'm going to want to try and implement this paper, which is about automatically debugging memory leaks in JavaScript programs. So the idea of this paper is you take heap snapshots at certain intervals, and then you essentially diff the heap snapshots and try and find points in the program where you have growing chains of memory. And if that is a situation, then you probably have a memory leak. And they do some very impressive stuff where they map these memory leaks back to precise points in the source of the program, which is really what we want to do, mapping the heap back to the source program if possible. Okay, thank you. Yeah, Ollie? I can repeat if it's faster.
You reduce the heap allocation by 25%, but does that actually produce a speed up? That's ultimately what you're interested in, is getting faster, right?
Well, allocations, the question is, I reduced the heap allocation of Tycoon app nodes by 25%. Does that make things faster or just make you use less memory? I mean, usually allocations correspond to how fast something is. Probably not that much faster. 25% of just Tycoon apps is not very much. It's not a noticeable difference, for example, but it's just every little bit you make, bit of difference you make does make improvement. And people make bug reports like GHC uses X amount of memory, so if it can make it use less, then I'm all for that. Neil?
Was there no thought to making a special type thing that was a Tycoon app, but with an empty, the empty list being implicit?
So I don't think that would help. So okay. I don't think that would help very much because you would save one word per Tycoon app, but you still have 2 words for the new constructor plus the info table plus a pointer to the Tycoon, and all the empty lists are shared, so they're not like the problem. So you save 1 times 150,000 or whatever, or 1 times 1.5 million words, which is maybe okay. That's decent.
But it might apply to more than just type, so you could get perhaps.
Yeah.
a broader
I mean,
coverage.
it maybe be decent. It just you have to trade. There's a trade-off between how complicated you make the compiler, which is already arguably complicated, and how much memory. I mean, you could do a lot more complicated things, right? You could represent things using just raw byte arrays and stuff, but you don't really want to do that unless you have to. So it's always a trade-off. Like, how high level do I make my program, and how much memory does it use, and where you draw the line depends on what your application is. Yeah, Tim.
Presumably the fix was really simple for that case, just to have a top level CAF.
Yeah. So the question is, surely the fix for this case is really simple. Yes, it was. all the fix was. So in GHC already has this smart constructor for type. It's called make Tycoon app, because function types are treated specially anyway. So in this smart constructor, we added a special case which checked, is the Tycoon equal to lifted type Tycoon kind, whatever. And if it was, then we defined one CAF, which is Tycoon app, lifted Tycoon empty list, so that they're all shared because it's a CAF. Yes, precisely. Yeah, Andor.
Hi, thanks for the talk. My question is, do you want to integrate GHC debug to any kind of IDEs?
The question is, do I want to integrate GHC debug into any IDEs? I'm not averse to the possibility, but I'm not precisely sure how you would. So if you have an idea for an interface, then talk about it. I have experience with Haskell IDE engine, and I can't think how it would fit nicely into the API. Okay. So, but it would be nice to have an interactive mode like GDB, but for GHC debug, I think. But that's a slightly different question. Yeah, Christian?
Was there any result of putting stuff into the compact region?
Oh, we haven't done it yet. The question is, did the compact regions make a difference? We haven't actually done that yet, because basically you can't put pinned memory into a compact region. And fast strings are backed by pinned byte array hash. So we first had to make the byte array hash unpinned using short byte string rather than byte string, which Daniel has implemented, but we haven't merged that patch yet. And then it's more work just to put it into the compact region and try it. I can't think how it would make things. I mean, the only way that I think it would make things worse is if it was too slow to actually compact the thing in the first place. because compacting something and preserving sharing can actually be quite slow. So, but other than that, I think even reducing the GC pressure would be absolutely massive. Okay, thanks everyone for the talk. Congratulations.